So, welcome back everyone. Today we're gonna go back to what we were talking about last time, and we're gonna try to see how scientists actually record and stimulate these membrane potentials. So there's two ways you can simulate the membrane potential. But before we actually go ahead and show those, it's important to see what exactly a graph of a neuron at rest looks like. So at rest, a neuron is simply at negative 60 millivolts. So say this is change in potential or potential difference, and we can make this time. So this is negative 60 millivolts, and this is always going to be, or somewhere in that negative 60 to negative 70 millivolts range is what's going to be the potential for the membrane at rest. So this is millivolts. So at rest, you would just see a straight line over here like that, right? I'm just going to dot it so it's easier to see that this is what it is. Okay, so what scientists do is they insert a microelectrode into the neuron. So let me just draw out the neuron. So this is the outside of the neuron. Obviously we have the nucleus inside. We have dendrites sticking out. And this is all anatomy of the neuron, which we'll definitely touch on later. But yeah, this is just a general understanding of what the neuron looks like. Then we have its axon coming out here, covered with myelin sheets. And obviously, there's a node somewhere over here. And yep, that's basically what the neuron looks like. So what happens is there is an electrode, or basically a thin conducting piece of metal that is inserted into the neuron over here, and another electrode is inserted over here. So now if you see, it's kind of like the neuron becomes part of the circuit. So this part of the electrode will be connected to a battery. So I will draw the battery out over here. Now we'll also talk about how the configuration of the battery will determine what is going on. And then over here we're going to see this side is going to be connected to a voltmeter. If this will delete, that will actually track the potential difference across. So in this case, notice how there is a difference between the size in this part and this part of the battery. So the bigger part of the battery will always represent the positive side, while the smaller part of the battery, or the smaller bar, will always represent the negative side. So in this way, we could have two configurations. We could have this one, where the positive is this over here, like on the outside, and the negative is facing towards the neuron. And in this case, what's happening is negative current will be going this way. So there's a more flow of electrons that way. Whereas in this one, since it's positive, and all the electrons will flow out. So these two configurations will result in two different types of graphs that are formed. Obviously, this is when scientists are putting in current or taking out current from the neuron. And this is how we get, polarization, which means, there's a change in the charge. So let's take, let's call this configuration 1, and let's call this configuration 2. So, and let me just color code it as well, why not? This will be blue. It's not a blue color. This will be blue, and this will be red, and we'll draw what's happening on this graph. So let's talk about the blue one first. Obviously, we're going to start here on negative 60 millivolts, I'm just going to draw it a little bit above just so we can see the difference. And now what's happening is I'm adding more current. I am making it more negative because negative current is flowing inwards. So if I were to stimulate it a bit, I'm going to see a sharp drop and then a return back when the stimulus is turned off, right? And if I start stimulating it more, if I start stimulating it more and more with a larger amount of current, or basically a stronger battery with more voltage, what I'm going to see is an increase in how much it gets negative. And slowly it's going to go even more negative and even more negative, and you get the point. And so just to, give you more of an understanding, I'm going to draw another graph or another line over here that will show you the change in current being supplied. So current is going to get, in this case, current will get more and more negative. So it's going to go like this. If I can get the correct color. It's going to be initially 0, and then it's going to go down a bit, and it's going to stay on, and then it's going to turn off. And then we'll keep going. We'll keep going, and then I'm going to turn it on with a larger amount of current flowing when I come back. I'm going to keep it off. I'm going to turn it on for a larger amount of current. It's going to go, and it's going to turn off. And then finally, a larger amount of current, and it's going to turn off. So this is how the change in potential is going to correlate with the change in current, or the increase in, say, a negative current. And this is called a hyperpolarization. Hyper, I'm sure you can guess, hyper means more. So hyper polarized, meaning it's getting more negative or more polar. On the other hand, let's consider number 2. So situation or configuration number 2 is almost the exact opposite. So what's happening is we're going to start over here, and then we're going to have a little bit of stimulating current come up. Shoom. And then the stimulating current is going to turn off, and then it's going to turn back on. And you see it's increasing because there's positivity coming in. There's a positive charge that's attracting the electrons to go out. So it's becoming less and less negative. So eventually it's going to start even crossing 0, and at some point you're going to see an action potential arise. This is what we're going to talk about in the next lesson. This is an action potential. But the general idea is, now I'll also show you exactly what the current is doing here. It's going to increase, positive current because it's going up, and then it's going to just keep increasing. So it's basically the opposite of the hyperpolarization. And this, if you might have guessed, this is supposed to be higher than that. This is called a depolarization. So a depolarization causes an increase in the polarization, which means it's getting less negative. Okay, so that's just polarization. And one thing that we might want to touch on, maybe in the next one, but I'll just introduce it here, is that eventually the depolarization is going to get to a threshold current, which means at this amount of current, it's going to elicit an action potential. We'll obviously touch onto that a little bit more later in a different lesson, but that's just a general understanding of what's going on when we're stimulating. So while we're on this topic of electricity, we should also just rehash what we've learned about diffusion and electrostatics. And I think it's high time that we actually define these two. So diffusion is nothing but the travel down a gradient, moving from lowest or highest concentration to lowest concentration. So this is really important when we're talking about the diffusing of potassium and sodium. And those are two pretty important ions that are used in creating a membrane potential. Okay, so just trying to reintroduce this idea. We have the diffusion happening, and we should consider what's going on inside and outside of the cell. And for here, we're going to just consider two particles, potassium and sodium. So in this case, we have sodium being more permeable to the membrane than potassium, meaning it can more freely move across the membrane than potassium can. And exactly this ratio is three potassiums will move for every two potassium, or 3 sodiums will move for every 2 potassiums. Sorry about that. So what I mean by this is there's going to be a large concentration of K plus over here, and it needs to move across this membrane. But as it's moving the more positive ions this way, so it's becoming more positive on this side, it's leaving behind a negative charge over here on the inside of the cell. And guess what? We have our handy dandy electrostatic force coming into play here. In this case, now that there's a separation of charge between positive and negative, some of these potassium ions are going to be pulled back into the cell. They're going to be pulled back into the cell like this. And a similar thing is going to happen with sodium, right? Something's going to move here. It's going to become more positive on the inside of the cell and more negative on the outside of the cell. There's going to be an electrostatic attraction, and sodium's going to have to move back out. So in this case, diffusion and electrostatics kind of like work together to create this potential, or this equilibrium situation where sodium and potassium are constantly moving across the membrane, but overall the concentrations inside and outside of the cell are not changing. And that's what we call the equilibrium. And this was kind of like founded by Nernst, who basically gave a general equation for how we can understand what's the equilibrium point of every ion that is permeable to a certain surface through the membrane. Exactly. So for example, let's take potassium. Let's try to talk about the potassium potential. So according to Nernst, I'll just write his name over here. The equilibrium potential, EK, of say EK plus, is going to be equal to 60 log K plus out. So this is the concentration of K plus outside of the cell, and K plus inside of the cell. Okay, so also known is, we could also rewrite this as another way. So we have RT over ZF times ln of K plus out over K plus in. And these two values are roughly estimated to be equal, but they're not necessarily equal because there's a base change between log and ln. But these are two ways you can represent what is the membrane potential when a certain membrane is permeable, or is, considering only that one ion, which in this case would be potassium. If you want, we could write it for sodium as well. It's going to be very similar. It's just going to be E of Na plus equals, say, I'm just going to use this one over here, RT over ZF ln Na plus out over Na plus in. And I'll just once again review some of the symbols that are used here. We have R being the universal gas constant, which is 8.314 joules per mole. We have temperature being in Kelvin. Z is the valency, or basically the charge or the number of ions. And F is the Faraday's constant, which is a big number. I think it's 96,485 coulombs per mole. Yeah, I'm pretty sure that's correct. But basically what this tells us is based on, like, okay, if we were to disconsider potassium, we can just understand how sodium is going to move across the membrane using the Nernst potential. But there's another more generalization we could do with Nernst potential, especially because, what's wrong with this idea? The idea is Nernst only considers one of the ions moving across the membranes. We needed to consider all the ions, and the main ions that I'm going to mention are sodium, potassium, and chlorine. All of these ions have to be taken into consideration when talking about the overall membrane potential. So, another group of neuroscientists, the Goldman, Hodgkin, Katz, they come up with a different solution, a different equation to better represent the overall membrane potential. And this is called the GHK equation. So the GHK equation is pretty long, mind you, and I hope you're ready to, really break this down, because, it's really similar to what we learned about with the Nernst potential. It's just a little bit more elongated. So essentially, E of Na plus K plus Cl minus. So this is taking into consideration of these three ions. It's taking into consideration when calculating the membrane potential. So this will be equal to the permeability of K plus times the concentration of K plus outside plus permeability of Na plus times concentration of Na plus outside. And here's a catch. Permeability of Cl minus times Cl minus concentration inside the cell. And this is simply because it's a negative ion, it's an anion, over the permeability of K plus times concentration inside of the cell plus permeability of Na plus times concentration of sodium inside of the cell plus finally Cl minus permeability times Cl minus outside. So let's note some of the differences here. Mainly, what's the new thing here? It's this permeability constant. These permeability constants are really, really, making a difference now. It shows a level of how permeable the membrane is to each of these ions. Because obviously, some ions are bigger and some ions are more charged. And so there's a different permeability for each of them. And mainly we talk about sodium and potassium, especially with the sodium-potassium pump, which, is kind of a gradient for just those two. But let's just consider, okay, let's say the membrane is absolutely not permeable to chlorine, or is absolutely not permeable to sodium. In that case, the permeability constant would be 0. Let's say the membrane was not permeable to both sodium nor chlorine. That means that the coefficient for these will be 0. And guess what? 0 times anything is 0. So what we're going to be left with is just the formula for the membrane potential that is permeable to potassium. And so we would just get, most literally, the Nernst equation for potassium. So we would just get EK plus is equal to, I forgot to put the actual constants in front of it, but it's going to be the same thing. It's RT over F ln, this entire thing. Oops. So it's just going to be RT over F times the permeability, and permeability cancels out in this case, so we don't even need permeability on there. ln, why did I write an E there? It would just be ln K out over K in. And I'll add that plus in. So that is kind of the understanding of what the Goldman-Hodgkin-Cox equation does. And once again, I just want to rehash, this is important because it gives more of sophisticated understanding when considering all the different ions that are present in this, in this membrane. So also there's something to note is, here, I'll just quickly erase this all first. Let's see. Clear. And then so considering all of what we have just learned, it's also, I might as well just write down what are the common ion equilibrium potentials. So for example, for K+, we're going to have a negative 80 millivolts, which represents that it's more concentrated inside of the cell because it's negative. We're going to have, for sodium, we're going to have a plus 60 millivolts, or somewhere in that region. And once again, this is when this is inside, this is out of the cell because it's positive. The sign matters a lot. And then chlorine minus is also negative 60 millivolts, or somewhere in that area. And this is, all of these is happening, and okay, this is also inside of the cell. But all of this is happening when there's a balance or equilibrium that's happening. And this is a steady state equilibrium that we're talking about, meaning everything is still moving, but overall concentrations are not going to be changed because the rate at which things are permeating is pretty much equal.